Hi, and thanks for tuning in. My name is Denis Shishkin, and I am presenting a paper titled Evidence Acquisition and Voluntary Disclosure. In many economic environments, people provide information in order to influence others' decisions. But if I want to convince somebody to do something and my agenda is clear, then making unsupported claims is hardly going to be convincing. What can be useful instead is providing hard evidence backing my claims. So it's not surprising that agents often strategically seek such hard evidence in order to persuade others. For example, entrepreneurs build and test prototypes of their projects to get funding from investors. Sellers certify quality of their products, and the workers take professional tests in order to get employed or promoted. At the same time, in many of these cases, there is no obligation to disclose all available evidence. So that, for example, when there is uncertainty about whether any evidence was obtained, unfavorable information could be credibly concealed. In this paper, I ask how to acquire hard information if it is disclosed voluntarily. Consider, for instance, the following example. There is an entrepreneur who wants to persuade an investor to fund a project. Project quality is continuous and unknown to both players at the beginning of the interaction. The investor invests only if the expected quality is above his privately known outside option. In order to persuade the investor, the entrepreneur seeks evidence about project quality. For example, she could build and test a prototype of this project. But suppose that testing yields hard evidence only with some fixed probability Q. For instance, this probability can represent imperfect reliability of the testing technology or the uncertainty in the time it takes to obtain the evidence by some deadline. If the entrepreneur obtains the evidence, she decides whether to disclose it or pretend to be uninformed. The investor cannot distinguish whether evidence was not obtained or was simply concealed. The main question now is, what is the optimal signal about quality for the entrepreneur to seek, given the probability Q? Let me now give you a preview of the main results of the paper. First, I show that if the probability of obtaining the evidence is low, then the optimal signal takes a very simple form of a pass-fail test that I call binary certification. The only thing that it reveals is whether the state is above or below some threshold. Note that this is despite the fact that the state is continuous and potentially any complex signal can be acquired for free. So this result highlights one channel that can explain why we often see simplicity of verifiable information in practice. The second result of the paper shows that under binary certification, the optimal threshold is strictly increasing in Q. In other words, the more likely is the sender to obtain the evidence, the more stringent will be the optimal certification standard. Now, to get some intuition for these results, note that there are two forces that affect the information that ends up being revealed to the investor. On the one hand, there is an information design force, because the entrepreneur ex ante decides which information to seek. This leads to an imprecision about high-quality projects, because providing very detailed information about them is suboptimal, since they are highly convincing to the receiver, and it's better to pull them with some slightly lower quality projects. In other words, this leads to an upper pooling of states in the equilibrium information structure. On the other hand, there is a voluntary disclosure force, because the entrepreneur also chooses whether to reveal the evidence in the interim. Sufficiently unfavorable news is concealed. In other words, this leads to lower pooling of the states in the equilibrium information structure. The main takeaway of the paper is that sometimes these forces can have a non-trivial interaction, and this interaction then leads to a simplicity of the equilibrium information structure. Let me now provide a more detailed model, results, and intuition. At the core is a variation of a standard sender-receiver game. At the beginning, both players are uninformed about the state and share some continuous prior mu naught with the mean theta naught. The receiver has an outside option omega that is unknown to the sender, who believes that it is drawn from some continuous distribution with a single peak density. The receiver takes a binary action, say accept or reject a project, and the sender always wants acceptance, while the receiver accepts if his posterior mean is above the outside option. So in order to convince the receiver, the sender chooses which hard evidence to seek, then obtains it with some fixed probability Q. If she obtains the evidence, she decides whether to disclose it or pretend to be uninformed by claiming to not have obtained it in the first place. The timing of the game is the following. First, the sender chooses an evidence structure, that is a mapping from states into distributions over messages or pieces of evidence. Then nature draws the state from the prior distribution, the receiver's outside option from the corresponding CDF, the realized piece of evidence E, and a set of available messages for the sender. I assume that the sender can always make unsupported cheap talk claims. However, in this setting, it is without loss to reduce all such cheap talk messages to a single null message, which can be interpreted as a claim that no evidence was obtained. It is always available to the sender. But with probability Q, the sender also obtains hard evidence, which means that she will be able to truthfully reveal the true realization of the chosen signal to the receiver. So at the next stage, the sender observes the set and chooses which message to send. Finally, the receiver observes the chosen message, his outside option, the evidence structure, and then takes the action. This talk focuses on the case that I call overt acquisition, meaning that the sender can actually commit to the way evidence is acquired. In other words, the receiver always observes the choice of the evidence structure. Under an alternative assumption that I call covert acquisition, the sender cannot commit to the evidence structure, so that the receiver does not observe the chosen signal if no evidence is disclosed. At the end, I will briefly talk about some recent results on the covert case and fully describe which results are robust to this assumption and which ones are different. For now, assume that pi is always observed. To analyze the model, consider first the disclosure stage at which the signal pi is fixed and common knowledge. It turns out that it's very convenient to take the so-called belief-based approach to analyze this subgame. In this subgame, disclosing a piece of evidence leads to some posterior mean, which is sufficient to describe the receiver's behavior and therefore the sender's payoff. The sender's payoff is equal to the probability the receiver accepts given the distribution of the prior, distribution of the outside option, and the signal pi. But since the receiver accepts whenever his outside option is lower than the posterior mean, the sender's payoff is simply the outside option CDF evaluated at the induced posterior mean. Therefore, we can associate every piece of the evidence E with the corresponding posterior mean, and each evidence structure with the distribution of the posterior means. It is then well known that such a distribution is feasible if and only if it is a mean-preserving contraction of the prior. So we need to determine now which realization of this random variable would the sender disclose in equilibrium, and how does it depend on the probability of obtaining evidence. Now it turns out that such a refinement-related problem with a fixed distribution over posterior means mu is actually a well-known disclosure game analyzed by Dai and Jung and Kwong. Now fix some receiver's belief mean conditional non-disclosure theta null. Now it's clear that it's optimal for the sender to disclose all realizations that are above this theta null and not disclose otherwise. So the sender is playing a cutoff strategy. Now to determine the equilibrium disclosure strategy, we need to check the belief consistency condition. So that given the cutoff theta null, the corresponding mean conditional non-disclosure must actually be equal theta null. The unique solution of this fixed point problem is then the disclosure threshold that depends on the evidence structure mu and probability Q. Moreover, since the receiver is more skeptical about non-disclosure when the sender is expected to have more information in terms of higher Q or mean-preserving spreads in mu leads to more disclosure, or equivalently, a lower equilibrium threshold. In particular, when Q is equal to 1, the receiver is fully skeptical because the sender is known to always obtain the evidence, and so there is going to be full unraveling in equilibrium, corresponding to the 0 disclosure threshold. The takeaway here for the further analysis is that the information is distorted due to voluntary disclosure. The sender seeks some information parameterized by distribution mu, acquires it with probability q, and then discloses it partially, which means that mu undergoes a two-step garbling, leading to a distribution of disclosed evidence that, compared to mu, is scaled by q and pulls states below the equilibrium theta null. Interestingly, these expressions turn out to have a closed-form solutions without restricting the prior if one takes the Rothschild-Stiglitz approach based on the representation of information structures in terms of convex functions given by the integral CDFs of distributions of the posterior means. Since this approach is also useful in the information design problems, this actually allows to solve the whole game. I don't have the time today to cover this approach, but the details are available in the full paper. Now that we understand how information is disclosed, the question is how is it's actually acquired. Let's start with the special case when Q is equal to 1. As I mentioned before, in this case there is unraveling at the disclosure stage due to the fully skeptical receiver. So there is no distortion of information, and the evidence acquisition problem is therefore equivalent to a pure information design problem. Such a problem in similar settings was previously analyzed by Colatiling and Dvorak and Martini. The key idea here is that due to the distribution of outside options being single-peaked, the sender wants to obfuscate high states. What that means is that the unique equilibrium, mu star, is going to be an upper censorship of the state. That is, there exists some threshold such that all states above this threshold will be pulled and therefore mapped into a single message, such that the state is good enough. And all states below will be perfectly revealed. The intuition is that the sender's objective is the CDF of the receiver's outside option, which is convex at the bottom and concave at the top. So it pays off to reveal more information about low states and less information about high states. This special case illustrates that absent voluntary disclosure concerns, the information design force in isolation leads to upper pooling of the states. So what about Q being less than 1? Well, the main results of the paper characterize how optimal evidence structure depends on Q for a general Q. First, I show that the equilibrium evidence structure exists and is unique up to an outcome equivalence. So the structure of this of optimal mu is characterized by a cutoff Q bar. When probability of obtaining the evidence is above this cutoff, the optimum is a two-sided censorship. What that means is that it has pooling at the bottom as well as pooling at the top. Moreover, the lower pooling threshold actually corresponds to the disclosure threshold under fully informative evidence structure, and the upper pooling threshold coincides with the pure design case we just considered. In other words, the voluntary disclosure and the information design forces that lead to two different pooling regions actually do not interact. In contrast, when the probability of obtaining evidence is below the cutoff, the optimum is a binary certification, which corresponds to a simple pass-fail test. Moreover, the equilibrium binary threshold is increasing in Q. Let's now look at the figure that illustrates how optimal evidence structure depends on Q. On the x-axis, we have the state space, and on the y-axis, we have the probability Q of obtaining the evidence. First, let's look at the very top of the figure. When Q is equal to 1, the solution is an upper censorship, so we have full separation below and pooling above some threshold. As Q decreases, the receiver becomes less and less skeptical when the sender claims ignorance. So that leads to more and more pooling at the bottom. As I mentioned before, the upper pooling region actually stays the same above the cutoff Q bar. This is because, again, there is no interaction between the two forces. However, at Q bar and below, there is interaction, and the sender actually switches to a binary certification, which can happen either continuously or even discontinuously. Why is this beneficial for the sender to switch to a binary certification? Well, this is because as Q decreases, the sender discloses less and less often, and the only way the sender can self-incentivize to disclose more often is by increasing the likelihood of obtaining sufficiently good news. Since on the binary certification, the sender always discloses pass, she effectively commits to disclose more often by making the upper pooling region larger. Moreover, as Q decreases, the sender compensates for lower likelihood of obtaining any evidence by increasing the conditional probability of obtaining good news. Finally, let me briefly discuss some recent results in a variation of the game where acquisition is covert. That is, suppose that the sender cannot commit to the evidence structure, so that if the sender decides to deviate to another evidence structure and then not disclose the evidence, this is not going to be detected by the receiver. Clearly, such a deviation might benefit the sender if the evidence structure she deviates to has a lower non-disclosure posterior mean than the on-path one. This is because the belief consistency is now required only on the equilibrium path. So there is less commitment, and the tools from the information design are harder to apply. However, it turns out that this covert acquisition game is also possible to analyze using a similar approach. First, note that when Q is high, the equilibrium is actually going to be the same. This is because the sender cannot benefit from the newly available deviation because the non-disclosure belief mean is already minimized. So what about the case of low Q? Let's now look at the following figure that illustrates the equilibrium evidence structure under covert acquisition. Note that main qualitative features of the equilibrium are actually the same as in the overt case. If Q is low, in particular, if Q is low, the equilibrium evidence structure is also a binary certification. However, there are two important differences. First, the cutoff is lower because now the sender switches to a binary certification only when the two pooling regions meet. Second, as Q decreases below the cutoff, the binary threshold will now be decreasing. This is because now the evidence structure must be robust to deviations that the receiver cannot detect. All else equal, as Q decreases, lower skepticism of the receiver leads to higher non-disclosure posterior. Since the sender's optimal binary certification threshold is increasing in the non-disclosure posterior, this leads to a more stringent certification standard in equilibrium.